OK, so now that we've gone through the beginning exercises of what a directory-based distributed shared memory machine looks like, let's talk about how to actually figure out where the directory is. So you have an address. And usually these systems, you're going to want to do this on the physical address basis. You're not going to want to do this on virtual addresses. You're going to want to have to run this all. And this is because you're sharing data between lots of different systems. At this point, you're sort of out at the system bus. These addresses are no longer virtual. You've gone through the translation look-aside buffer or the MMU, and you've figured out what the physical address is. So to figure out what the directory is, or what's sometimes called if in a distributed shared memory machine, the home node, or it's a number of which one of these directories to go to. And there's a lot of different ways to do this, but one of the more common ones is to just use some bits out of the address. So you take the number of directories in the system, take the log base 2 of that, and then you take that number of bits to be the home node number. So when you take a cache miss, and it's not in your cache, and you need to go figure out and do the load of that data, we'll say you send a message, and the message ID and the destination of that message will actually be the home node. And hopefully your interconnect knows how to route the data to that directory. Now, taking the high order bits has some benefits. Let's take a look at that. As we discussed already in a non-uniform memory access architecture, the OS can control the placement. It can do this because based on these high order bits, you can actually determine which node in the system or which directory in the system you're going to. So you can actually basically allocate memory, allocate your stack, allocate your instruction space based on the physical address, and the OS can manage that because the OS has absolute authority over where physical addresses get doled out to. Downside is a directory or a home node can become a hotspot. So let's say all of a sudden, all of your processors in your system try to access one page of memory. There's like a hot page which has all the locks in the system, and you're in some threaded program, and you have to go access those locks a lot. Well, if you look at that, that's all going to be down here. It's going to be sort of low-order addresses. It might be from sort of here down, whatever your page size is, we'll say. So even if you're not having false sharing, anything like that, you typically would try to pack all the data onto a page or a structure or something like that. And it's pretty hard to interleave it based on the very high order bits of your address. And especially considering a program that has effectively no control of the high order bits of a physical address that's managed by the OS. So if you do this, one node can become a hotspot because these will all alias to the same directory. So all the messaging traffic goes to one node, and this almost starts to turn back into a bus. Now, we have one directory. All traffic has to go there. It's a little bit better because we don't necessarily need to invalidate all other locations, but the directory and the bandwidth in the directory starts to become critical. Well, that's a tough one. The flip side is you can start to try to have the low order bits determine where your directory is or which home node you're using. So you still have the offset within a cache line, but then you have the number, the bits of the physical address that determine what home node you're going to be the low order bits. Well, this ends up being very well load balanced because you're going to choose different home nodes effectively at random, depending on which cache line it is. So two cache lines will, the same cache line will go to the same home node or the same directory. But if you have slightly different cache lines, which is pretty common because it's pretty hard to contend all on one cache line. There's just not that much data in one cache line. You'll spread across the different controllers, and you'll effectively have some good distribution. Flip side, though, is the OS loses placement ability here. So it's tricky. It's a tricky trade-off here to think about. Some people have even built systems where it's configurable. This gets a little bit more advanced, and I touched on this in the last slide of today's lecture, but you could think about having some systems where, depending on the actual address and depending on what comes out of your page table, maybe making different choices of how to do the mapping. But everyone has to agree on the mapping, which gets a little bit tricky because the directory has to agree on the mapping, and all of the caches in the system have to agree on the mapping. OK, so let's take a look at what is inside of a directory. So we added this new hardware structure. And whenever we add a new hardware structure, I like to look at all the bits inside of the hardware structure. So we add a new hardware structure, and this hardware structure has an entry per cache line in that particular memory connected to the directory. So if you were to look across the entire system, there will actually be an extra piece of data for every single cache line in the system. And the naive approach for this will have it such that every single cache line in the system, whether it's, or excuse me, not every single cache line, every single memory line in the system. So if you have 10 terabytes of memory in the system, the naive approach is going to have a directory entry for every single block size chunk of memory, cache block size chunk of memory in the system. And these are held in big tables. Typically, they're held in SRAM. You might try to put them in DRAM. And what do we have here? Well, the directory needs to know what state the cache line is in. And we're going to look at 3 different states in our basic protocol here: shared, uncached, and exclusive. So everything starts out as uncached. It's out in main memory. When it gets pulled into a cache as read-only, the directory is going to say, OK, that's now shared. If it gets pulled into a cache read-write, the directory is going to note that as exclusive. Now, if it's in shared or exclusive, we need to know what node. Well, if it's exclusive, we need to know uniquely what node has that, so we can go message it when we need to go and validate it. And if it's shared, we need to know the list of all possible places that it could be that we're going to have to send messages to. And this is better than having to broadcast or send messages to all the nodes in the system. So we're going to have what's called a sharer list here, which is in a naive full map directory is going to have 1 bit per core in the system or per cache in the system. And it's either just going to have 1 or a 0 in it. So if it's a 1, that means that core has a share or a read-only copy of the data. And when some other cache goes to get it in writable in its cache, it's going to have to invalidate, let's say, this one's or the 0th core's cache. Now, if you're exclusive, you're not going to have multiple bits set here, because this basically means that that core has a writable copy, and we can't have, if we want to keep the data coherent, we don't want multiple writable copies in the system. So as we can see here, it's denoted only 1, 1 here. And if it's uncached, we don't need to track anything there. We just get don't cares. There's one other state here that I have, and it's pending. And this usually actually turns into a couple substates. There's different ways to track this. At the directory, these transactions take multiple steps. You're going to send some data and start transitioning. Let's say you want to get a data writable. Well, the directory is going to have to invalidate all the other copies. It can't do this instantaneously, but we want to provide the appearance of atomicity, or that the operations are atomic in some way. So typically, you'll actually have some substates that are stored here, which are something like, oh, this cache line is currently transitioning from, I don't know, U to E. Don't allow some other transaction to happen to it right now. And it's just kind of block that. Another way to do that, one way is to store it actually in the directory as a state bit. Another way is you have some fully associative structure, a side structure, which just has all of the cache lines currently in flux. And the directory is smart enough to know that if some other request comes in for that line while it's in flux, just to NACK that request or negative and acknowledge that request and tell the other cache to retry. So you can do it either way. But it gets pretty complicated. We're not going to talk about all the details of that, but we'll talk about the high-level transitions here and assume that they're somehow atomic. So here, we're going to look at how MSI fits together with this. But you could actually think about doing this with MESI or some other protocol. It's a little bit simpler. MSI is a little bit simpler, so we're going to look at that. Also, the benefit of something like a MESI protocol is lessened in a directory, because if you were to pull something in the exclusive state, which is unmodified at the beginning, and then someone else wants to get a read-only copy, you're basically going to have to send a message to that core. And that was inexpensive on a bus because it could just see the transaction going across, and it would just snoop it and would demote from E to shared or something like that, E to S. But now it actually turns into actual work. The directory is going to have to generate messages, and you're going to have to wait for responses coming back from a cache which had it in exclusive. So full MESI is a little bit less common when you start to go to these distributed shared memory protocols. OK, so this is a slide that we had before. This is MSI on a bus. Well, things change a little bit when we go to MSI for directory coherence. And before we go through this, I wanted to point out that there's actually two different state machines going on here. There's one state machine which is happening in the cache controllers, so actually in the cache of a respective processor. And then there's a different state machine which is happening in the directory. And you'll see they'll have different letters here. This is SU and E versus MS and I. And we label these differently on purpose just to not get horribly confused. And these state machines interact by sending messages between each other. And as messages flow between the directory and the cache, they will be both going through different state transitions on these two tables. OK, so let's jump into this. This is the same modified, shared, and invalid states that we have in our bus-based Snoopy MSI protocol. We didn't change anything here. And the rules are the same. If you have it modified, you could do a write to this and not have to send any messages. If you have it shared, you can read the data and not have to contact anybody. If you have it invalid and you want to do anything with it, you probably need to contact somebody. Or you have to go contact the directory. Before, we would have to send a transaction on the bus. Likewise, the transition from S to M or M to S, we have to communicate. That was the same. So think about this as the same state machine except running on a bus, where before we would send transactions across the bus. Now we're going to take those transactions and turn them into messages that we send to the directory and messages we receive from the directory that we have to respond to. So before, when we were snooping traffic across the bus, which caused us to transition different locations. So here, other processor has intent to write. We saw that across the bus. So we had to transition ourselves to the invalid state. Now, we're actually going to get a message from the directory controller. So let's walk through this. But it's almost exactly the same as what we saw before. So this is the cache state for a particular line for processor P1. We'll start with the entry points. We start off in invalid. And let's say we want to get a readable copy of this line. So we're going to take a read miss. So what we're going to do is processor 1 is actually going to send a read miss message to the directory controller. And during that time, it does not have a readable copy. It cannot go and access the data. It's effectively still in the I state. Sometimes people will actually have sort of a pending state here, depending on how you go to implement this. It depends if you have a side structure, something like a misstatus handling register, where you'll track that in, or you can actually track it in the cache state itself. So you have a read miss. You send the read miss message, and you're waiting for a response. And this response is going to have the data that you need, and that's going to be a synchronization point saying, OK, you're safe to transition to S. OK, that seems pretty simple. Similar sort of thing here for a write miss. If we're in the invalid state and we do a write, we're going to send a write miss request to the directory controller. It's going to do something. And we may have to be waiting for a while here, because it might have to go invalidate all the other lines in the system. And then it gets a response. Once it gets a response, we have the data, and we can transition to the modified state. So as we said, these arcs are pretty easy. We can read by P1 and nothing changes. Or we can read or write if we're in the M state by P1, and we don't have to communicate with anybody. But now we have a few different messages coming in here. If we're in the shared state, we have to be responsive to an invalidation message, which is a little bit different than a bus snoop. So before, we saw another processor trying to write. That's what transitioned us to I. But now, the directory controller sends us a message, which says, invalidate this line. And that will transition us to I here. Note, there will probably be a reply. We will probably have to send a reply, because the directory controller wants to know when all of the cache lines in the system have been invalidated. And it might take a variable amount of time, and it's sending messages, so it wants to wait for replies to come back. So we're going to have to send a reply. So this arc here is similar, except we need to write back data, because we had modified data. We had writable data. We get an invalidate message from the directory controller. So we need to write back the data and then reply afterwards. Similar sort of idea here. OK, so that leaves two arcs left here in the middle. We're in shared, and we want to do a write to that cache line. So our cache we have in the shared state, we want to do a write to it. Before we can actually do a write, we have to send a message to the directory saying, I'm doing a write miss here. I want to get this data writable. And we have to wait for a reply before we transition here, because we have to wait for the directory controller to go communicate with all the other caches so that they don't have read-only copies, and we can have a writable copy. So it's going to invalidate all the other readable copies in the meantime. And then finally, we have an edge coming this way, which is from modified down to shared. And this is a little bit different. Well, it's the same idea here. Another processor is trying to do a read. So we have it in the modified state, and another processor tries to do a read. So we receive a read miss message. We don't need to invalidate the data, but we need to write back the data, because we have the most up-to-date copy, because we had it modified. So we're going to write back the data, and that's going to be a response. And then we're going to transition to the shared state. We can keep a read copy of this, because the other core is only having a readable copy of it also. OK, so that's any questions about that so far? OK, so two interesting arcs that we're going to add in here is this one and this one, which we didn't have in our base MSI protocol. And you may not need these. But what these correspond to is if our cache has the data in it, and then because of, let's say, a conflict miss or a capacity miss, it gets bumped out, it might be a good idea to go update the directory and tell the directory that in the future, if some other cache wants to go get that data, that doesn't need to go contact you again. So if it's in the modified state, we can write back the data, because we have dirty data. We write back that to the directory. And then we notify the directory saying, we don't have a copy of this anymore. You can transition to having it uncached. Likewise here, if we have a read-only copy, we may or may not want to do this. But if there's extra bandwidth on the interconnect, we might want to send a message when we do an invalidation here. And this is not an invalidation because of an invalidation message, but this is an invalidation because it just gets bumped out of the cache. We may want to notify the directory saying, please remove us from the sharer list. And if the sharer list is already empty, the directory might change the cache line from shared to being uncached completely. But I do want to point out these are not strictly necessary. The reason they're not strictly necessary is if we build the cache controller system such that if you're in the invalid state for a particular cache line and you get some message coming in that would have been, let's say, this message or that message or some other arc, we can just reply back saying, yeah, we don't have it anymore. We're invalid. We don't really care about that transition. So if you're here, the only message that's going to come really to you is an invalidation message that would just take you to the state anyway. So we can just ignore the message or just reply the same as we would to the normal invalidation message. OK, so directory state transition looks a little different here. We have uncached, shared, and exclusive. And as we said, shared means there could be multiple read-only copies in the system. Exclusive means there's only one cache in the system with that data. What's interesting here is if you were to actually have a MESI protocol running, that would not change the protocol running in the directory, because exclusive here is effectively the same state with respect to how the directory sees the line. It wouldn't have to do anything different. OK, so let's walk through a few transitions here of the state of the cache line in the directory. And this is not in the cache. Let's start off uncached. And let's say we get a message which is a read miss from processor P. Well, we should transition to S now. We should give it a readable copy. And we should reply with the actual data. And we should put P on the sharer list so that we know that if someone else needs to go invalidate that line, we need to go contact P. Now that we're in the shared state, let's say there's other read misses from other Ps, other processors here. Well, we're going to give it up the data, and we're going to add it to the share list. So we're going to take sharers and add to it the processor. The share list is just going to grow. OK, let's start here and go the other way. We're in uncached, and all of a sudden, we get a write miss from processor P. Well, we give it the data, and the sharer list or the owner list is going to get P uniquely onto it. And we're going to give it in the exclusive state, because we were uncached before. We don't have to contact anybody else. Let's look at this arc here before we go to these. So this is a little bit different, quite a bit different than what we had in these slides, because it's doing something different. But in this state here, we know, let's say, processor P0 has the data exclusively. But all of a sudden, a different processor, let's say processor 2, goes to access the data. Well, we already have the data in the exclusive state. So we're going to stay in the exclusive state, because some other cache is going to want to get it exclusive, but it's a different cache. So what has to happen here is we need to go invalidate the data out of P0. P0 is going to write back the data. It's going to transition to the invalid state. We need to then provide the data to the new processor P2, we'll say, and add that P2 to the sharer list. So we can transition into this state. And then finally, let's look at the edges between these 2 points. Actually, let's go this way first. If you have data that gets written back, so this is that arc which I said is similar to the arc here, which is optional. Let's say you have data that gets written back here. Actually, this arc may not be optional. Let's think about that for a second. This arc may not be optional. No, it's still optional, because you can just knack the message effectively and tell it that it's in main memory. OK, so let's say you're here, and you see a data write back happening. So a message gets sent to you, which is the equivalent of this arc here. The data was writable, it was exclusive in some cache, and it's no longer writable. It's probably a good idea to go contact the directory, write back the data, and clear the sharer list. So the sharer list is just empty, so it knows that no one has a copy of it at that point. OK, few other fun edges here. OK, we're in the shared state. So we have multiple read-only copies. And one cache comes along and says, oh, I need to do a write miss message. I need to get it writable. Well, now we actually have to go through a pretty long process. We're going to walk through the entire sharer list and send messages to all the sharers in the sharer list saying, invalidate this copy and tell me when you're done. We're going to collect all the responses at the directory. And once all the responses have come back, we know no one else has a readable copy. We can give the data value to the requester and add it to the sharer or owner list. OK, last arc here is from E to S, this orange arc. And that happens if we have a particular line as writable in one cache and another cache wants to go read it now. We'll send a read miss. The other cache is going to downgrade from E to S, or excuse me, from M to S in its local cache. But the directory is going to transition from E to S here. And we have to go get the most up-to-date data from the node. So we're going to send a fetch request to the node that had it before an exclusive. Once we get the most up-to-date data, we can forward that to the new reader and everyone, and we add that processor to the sharer list. OK, so questions about that one so far? These do start to get a little complicated because you have multiple state machines interacting. OK, so we're going to speed up a little bit here. I included this chart from your book just to give you an example of, we went through very quickly here all the different messages. And this chart here sums up all the different message types and from who they could go from and who they could go to. And this is in your textbook. And sometimes messages need to communicate addresses. Sometimes they need to communicate data. Sometimes they need to communicate which node the message is coming from to add it to the sharer list. But I'm not going to go through this into great detail. One thing I did want to say is these message types here do not include ACKs and NACKs. So when you go to request something, there's replies that come back. These replies after, that's not drawn in this diagram. We see data value reply, but that's just actual data. There's not like a response coming back from the sharer acking the share, or acking the invalidate or something like that. Another type of message that's pretty common that is not drawn here is a negative acknowledgement. So it's pretty common that if you have a cache line that is being transitioned, there's an appending state at the directory, and you get a request coming in, you might need to tell that cache, retry later. I can't handle this case right now.